Hey guys, welcome to the first video in the Orgo 2 series. So this one is going to be covering the very first topics you guys are going to be learning, starting with molecular orbitals. So you guys may have heard something like this in terms of like atomic orbitals from Gen Chem. So we're going to have to go over what molecular orbitals are. And trust me, it's not going to be as bad if you didn't like atomic orbitals in Gen Chem. You're probably going to find it's not too bad. All right, so let's get started. So first, what's a molecular orbital? Well, you guys heard of atomic orbitals, right? These are orbitals associated with one atom. A molecular orbital is the orbitals associated with the entire molecule, right? And so, what exactly is the show? Well, this idea is going to be prevalent for the idea of what we call a diene molecule, which is going to be the major focus of your the first new reaction you're going to learn in Orgo 2. Right, so what is a diene? Well, a diene is a compound with two double bonds that are conjugated to each other. So let me just show you what that's going to look like. All right, so if we have this compound right here, 4-carbon chain, and we have these two double bonds right next to each other. This is going to be called a conjugated double bond system. Now, why is that? So remember that double bonds are composed of p orbitals, right? And so if we were to draw the orbitals for this, I'll draw the carbons so you guys can see them. Here's our 4 carbons. I'm not going to draw the hydrogens, and I'm going to draw these little balloon shape. And then here's the other half of them. Okay, so these p orbitals, these like little dumbbell shaped looking kind of balloon animal things, these are going to be what forms our double bonds. Now the key thing to see is I've colored half of them red and half of them blue. It's very important that you see that the red ones are sort of lining up with each other like this, and that the blue ones line up with each other. This p orbital overlap is what gives us like the double bond character. So that's called a diene. All right, and we can of course have more. We can have something that looks like this. You can even have longer ones. So we can have double bonds looking like this. And the important part is that the p orbitals along all those carbons overlap. So it's going to look like this. So you see that they're all overlapping with each other. That's the point of conjugation. So if I had, let's say, some compound that looks like this, the orbitals would end up looking like this. And you can see that right here is a break in the double bond. We don't have a conjugated system here, at least with the whole molecule. So what this is going to show is these p orbitals overlap, but not those. Okay? And so what this means in terms of something that may help you guys understand a little better is we cannot resonate any of these double bonds over to this side because there is no overlap with the p orbitals on that carbon. All right, so that's the key thing to see here. And another thing, just in case maybe it comes up, we have other types of sort of classes that have like double bonds. So you saw the diene or the conjugated diene, something like this, right? What I showed you before, where the double bonds weren't able to get each other. So in this case, almost, this is called an isolated diene. And the last one you guys may encounter is something that looks like this. This is supposed to be a carbon. So if I just colored all the carbons, 1, 2, 3, 4, this is called accumulated diene. You could also here called an allene. And these are when the pi bonds are directly adjacent to each other. And so these are pretty unstable, but the main focus is the diene itself right here, this conjugated diene. All right. So what we're going to have to do is we're going to have to draw molecular orbitals for the diene. All right. It's not going to be that bad, but first let's talk about how we can even make a diene. So we typically use these allylic halides, right? So here I have Br here, right? And remember, we call it kind of an allylic halide because watch, if I have this guy leave, here's a double bond and here's your carbocation. Remember, the allylic carbocation can resonate, and we can have it look now like this, okay? And so that's going to be what we would use to prepare it, but how would we do it? Well, the whole goal, remember, is to make the diene, which looks like this, right? So we need to form a double bond right there. So what we would do is we would use a base like terbutoxide. So right here, and then it would take the hydrogen from here. This collapses down to kick the bromine out. And now we have our conjugated diene. All right, and the reason I use the bulky base like terbutoxide is just because if we used something like some other sort of basic, maybe a smaller base, you could have competing SN2 reactions. But so it's always just a safe bet to use terbutoxide in that case. Okay. And another way you could have done it is if you have a bromine here and here, right? So this looks almost set up like we did with our alkyne reactions, but you use terbutoxide, you'd again get the same. You'd get this. Okay. So now, how do we draw molecular orbitals when it comes to these compounds? All right. So we're going to start off with a very simple example, which is the original diene I showed you, just this one right here. All right. This is just going to be a butadiene molecule. So butadiene. The butas is the 4 carbons, and the diene tells us we have two double bonds. Okay. And so let's clear some space. So here's our compound right here. Here's our 2 double bonds. We're going to draw the molecular orbitals for this guy. So how do we do this? Well, the thing that to know is that we can have multiple molecular orbitals. All right. I showed you guys before where I drew all the p orbitals perfectly lined up. Red to red, blue to blue. This isn't always the case. We can have mixing and matching, all right? Oh, and I missed one. Okay? So, how are we going to draw this guy? All right? So, the first molecular orbital to draw is always the easiest one, right? And so this is going to be when all the p orbitals overlap. So you see how I drew it all the colors lining up? This is how we're going to do it. So I want to draw right here these balloons. We have 4 p orbitals, right? All of these carbons have p orbitals because they're participating in the double bonds, and therefore we have 4. Okay. Remember that this doesn't mean this isn't based on the amount of total atoms. It's just the atoms with the pi orbitals, the p orbitals. Okay. And so we denote the first molecular orbital with this symbol. We just write pi 1. Okay. And what you're going to do is you're going to draw this line next to it, and I'll explain why in a second. So what we're going to do, we have to show that this is the simplest one, right, where all the colors overlap. Now, if you're doing this on paper with pencil, what we're going to do is just going to shade it. So I'm going to color the top part white, and since we want to show everything overlapping, all of them will get white at the top, and then the unshaded ones will be a separate color technically. Okay, and so the first molecular orbital where we have everything overlapping, this is going to be the lowest energy orbital. All right, and so this is why you want everything to overlap, because overlapping orbitals are what we call they have a constructive effect. They're good. If we have a if we have orbitals that do not overlap, so if I had this and I shaded one white, and now we have this, you can see that the top one is unshaded and one is shaded. These are not overlapping, and these have a destructive effect. Okay? So the lowest molecular orbital is always the lowest energy and the more stable one. Now, what is this line over here? So what we need to do, what this line is for, is to show how many electrons we have. So we have 4 p orbitals, and you see that we had the 2 double bonds in them, right here. This one, this one. Each one of those double bonds has 2 electrons, and so we can think that this atom has one of those electrons in the p orbital, this one has another for that carbon, and another for that carbon. So that's a total of 4 electrons. 4 electrons. Every one of these little lines over here will have, we fill it up with 2 electrons. All right, you always fill the lowest one first. All right, and then we go into the next ones, but we'll worry about that later. So now let's go on to the next molecular orbital. So this is going to be pi 2. So remember, as we go up, energy is going to also increase. So now, again, draw all 4. You're always going to still have the 4. All right? And so now what's going to happen? So one thing I didn't mention is this idea of a node. I showed you guys what this little example right here, where I had one shaded and one kind of wasn't when they're next to each other, this destructive overlap. So when we have this example, what we do is we put this little dashed line between them, and this is called a node. All right? So this node, we essentially separate those orbitals that do not overlap properly. So always the thing is that the lowest molecular orbital, the lowest energy one, the first one we draw, this one has 0 nodes. All right, so you can see that everything overlaps, no node. Every time we go up 1 molecular orbital, we increase the amount of nodes by 1. So here we're going to have, let's clean this up a little bit, 0 nodes. Now we're going to have 1 node. Okay? And let me move this down a little bit. And so keep that idea in mind. Every time we go up 1, it's going to increase by 1 node. And you always need to make the molecular orbitals symmetrical. All right? So what does this mean? Where do we place the node, right? This like dashed line somewhere. Well, you're going to have to keep the overall molecular orbital symmetrical. So if we put it here, what this means is this is going to be shaded white, and now these are going to be shaded this way because they have to be the opposite of what that other node was, of what was on the other side of the node. That's not symmetrical. So we're going to move this node, and we're going to put it right down the middle, because now these are going to be shaded in the same color, and these will be shaded the opposite. Okay? And so you can see that in the first molecular orbital, everything overlapped. This is the most stable form. Now, the second molecular orbital, these 2 overlap, and these 2 overlap, but not all 4 together. And so we have the 1 node. Now we're going to go on to the next orbital, molecular orbital, pi 3. And so again, draw all 4. And a little trick, if you don't know how many molecular orbitals you're going to have to draw all of them, is going to be figure out how many p orbitals you have. So we had 4. The maximum amount of molecular orbitals you're going to just have to draw is going to be the amount of p orbitals minus 1. Minus 1. So we have 4 p orbitals. Oh, sorry, not that. What we do is we draw the to help you figure that out is we keep going until the amount of nodes is 1 less than the maximum amount of carbons, maximum amount of p orbitals. So we have 4 p orbitals. So we're going to go until we have a molecular orbital with 3 nodes. So we have 1 node. We're going to have to draw 2 now. where we're going to place the second node. All right. So again, remember, we need to keep it all symmetrical. So if I put one node here, that means again, this is shaded, and all the others will have now opposite shading. But we still need to put one other node. So what I'm going to do is I'm going to put it right here, because now the one on the left will be shaded at the top. We shade these downward, and this one is going to be top. So remember, when you have a node, the next p orbital you draw must have the opposite shading. Shade white at the top, node, shade white at the bottom. Okay? So that's two nodes. And so we're going to keep going until we have the amount of a molecular orbital with nodes one less than the amount of p orbitals. We have 4 p orbitals, so we're going to go until we have 3 nodes. Pi 4. So this one's going to have 3 nodes. So we have to put 3 nodes. Remember, you must keep it all symmetrical. So how are we going to put 3 nodes? You can put one here, and one there. Shade this one at the top, bottom, top, bottom. So you see there is no overlap from any of the orbitals. This is always going to be the highest molecular orbital, which is also the one with the highest energy, so it's the most unstable. So the trick that I liked when I was doing these is the 2 easiest orbitals to draw is always the lowest energy one and the highest energy. The lowest energy one is always 0 nodes, so draw the amount of p orbitals you have and shade them all in so everything is overlapping. And then draw the highest energy one. So you draw all 4 of the orbitals in this case, or more if you have another kind of conjugated pi system, and you draw everything so that none of the p orbitals overlap. All right, that's going to be the second easiest one, and then kind of fill in the middle. All right, and we'll do example problems with different kinds of compounds so you guys get used to that in a future video. So we have all 4 of the molecular orbitals drawn. Now what we have to do is fill in this area here where the electrons are supposed to go. All right, and so again, we had 4 electrons. Every one of these orbitals gets 2. So you always fill one row before you go into the next one with the maximum amount of orbitals. So I'm going to put 2 here, and the way we do this is we draw these like arrows that kind of look like the radical arrows you guys drew. And because of the way like the orbitals work, one electron is going to be facing like an upward arrow, the other one gets a downward arrow. Okay, so those are 2 electrons. Now we're going to go on to the next one. So we have 2 electrons here, and we're done because we've used up the maximum amount of electrons. And so now, before we end the video, I'm just going to mention one other point. The highest orbital that has electrons is called the highest occupied molecular orbital. And what we do is we just shorten this name by writing HOMO. So highest occupied molecular orbital. And then this orbital that's right above the electrons, right above the orbital with electrons. So this one is going to be called the lowest unoccupied molecular orbital. Because you see, it's going to be unoccupied, and it's the lowest of all the unoccupied ones. So we call this the Lumo orbital. Lowest unoccupied molecular orbital. So the Lumo, is always above the HOMO orbital, right? And these will be very important when talking about the first reaction you guys are going to be learning called a Diels-Alder. All right, so I'm going to leave it for this video. And the next video, we're going to go into some examples that are more of just drawing molecular orbitals, so you guys see a bunch of different sort of scenarios, all right, and get into a little bit some of the trickier things. All right, I'll see you guys in the next video.